Physics in the choice group. I'm very pleased to be here. I want to talk about the mechanics of markets today. A lot of this stuff has I think, been developed in mathematical finance, but I'd like to take a sort of philosophical foundational stance on it. This is a particular way to look at how a financial system is built, what it consists in, and what it does. And I hope some of the philosophical upshots of it will become clear as we go. I thought I'd start with some inspiration here. So a wise man once said, the desirability of moving in the directions of greater realism is not surprisingly widely recognized, but the way in which I want to do so is different from the direction taken, for instance, in behavior economics and psychology of judgment and choice. But the aim is not to describe the way in which we do, in fact, evaluate prospects and make decisions, but to describe how we should, given our limitations and constraints. This is, of course, our hero, Richard Bradley.
You're taking out the grammatical errors.
So I'd like to talk about a certain framework for analyzing finance, which I think emphasizes some of our limitations and constraints, and also embraces some of the ways in which we don't exactly accurately describe almost anything when we model it. Here's a warm-up to get started. This is from classical mechanics, done at a picturesque level most of the time. Classical mechanics, when it was built, it had an ontology. That there were certain things that the world were said to consist in when Newton wrote down his equations, his laws. For example, there were masses, and there were forces, and those forces pushed around the masses. The forces were a tendency to move, the masses were a resistance to change. There were lots of different kinds of forces. Here's one that's just shooting along with constant velocity. But there was a systematic way of describing the relationship between the forces and the masses. That relationship was really more of a mathematical framework, which can in principle be separated from the ontology. So classical mechanics, when it was built, had an ontology associated with it, but we can extract out really what the framework for formulating classical mechanics is. And this has been done in lots of ways. We write down F equals ma. This is maybe the most familiar expression of classical mechanics. Force is equal to the mass times the acceleration of the object. And this equation, although it applies when the ontology is forces and masses, the same equation applies in modern general relativity, where an inertial frame is a geodesic and the force is something pushing you off the geodesic. It applies in quantum field theory. It applies in many different contexts. Okay, so there are analogs of this formula all over the place. It doesn't need to be connected to the ontology. Those familiar with more mathematized approaches to classical mechanics might be familiar with Lagrangian mechanics or Hamiltonian mechanics. These are really, originally they were all describing the same sorts of things, but they were different frameworks. Lagrangian mechanics focused on a certain sort of optimization problem, where you would find a certain quantity associated with a physical thing, which we call this action, and you would extremize that quantity, and that would tell you what the thing would do. This is such a general idea, of course you would expect now to see extremization problems all over the place. Again, in general relativity, if you're looking for geodesics, you want to extremize. In economics, one extremizes all the time. You want to optimize and extremize, for example, utility function. Hamiltonian mechanics, again, we were often describing the very same things, but it's a different framework. And the central principle of this framework is that trajectories admit conserved quantities. Whatever's happening, whatever change is happening, is a conserved quantity that carries you along it. So for the newcomers to this sort of thinking, I'd like you to humor me for a moment. I'd like to say this for the choice group because you guys may object as I get going, but just for a moment, humor me, okay? Suppose a quantity, let me call it x, and let it be the log of some other quantity p, changes over time according to Newton's equation with F equals 0. So no force. And then this would be Newton's equation in that case. This is just a, that's the acceleration, for 0 force. And now suppose we interpret p as a price. This is just numerology right now. It doesn't have to be anything deep. Then we can make the following observation. When this holds, again, I've got a sort of funny thing here. I've got x is equal to log p. I'm going to look at what happens to the price. When this holds, well, it's really equivalent to this statement. The price goes in this exponential way for some r. This is a simple little calculation you can do. Acceleration to 0 implies this. Whoops. There you go. No worries. You're good. You're good.
Keep going again.
It implies this familiar equation. This is the equation for a particle moving with constant velocity. So when x is equal to log p, we get p equals to e to the x, and thus, right, this thing comes upstairs. You end up with this equation that looks a lot like something accumulating interest, for example, if r is positive, or deteriorating its value if r is negative. So you could say something like this, again, if you were just doing numerology, like writing down this equation this particular way and saying there are no forces is equivalent to saying that price changes with something like what people call the time value of money, or the time discounted value of money. One can observe just empirically that when people give each other loans, the fact that they have to wait to get their money back, they interpret as a cost to them, and so they charge money for the loan. And that if one were to continuously compound this charge, you would write something down just like what I wrote before. Whoops, where is it? There. You'd write something like this down in order to model it. So you could just take this as a descriptive claim. But it is meant to be suggestive, and the thought then is that maybe the frameworks of classical mechanics that I've sort of just written down could be used to model financial markets more generally. Our question really today is, can they do that? And the thesis of the talk is just yes. So that's what I was trying to argue for. Is this mine, by the way?
Yes.
All right, thanks. So simple. This is what I want to try and do. We did our warm-up. I'll talk a little bit about some random finance, in particular random walk approaches to finance. I'll then introduce this idea of trade space that I'd like to. This is sort of an interpreted way of thinking about classical mechanics as a framework for if And then I'll end with some comments on market dynamics, how dynamics look in this context, and just briefly say a few things about applications if we get that far. For the dynamics, I might switch to a whiteboard, but it might be easier then. Okay, so that's the plan. Let's talk about finance a little bit. In particular, just some very general comments about the foundations of stochastic modeling in mathematical finance. So I'm using physics here to think about finance. A lot of these techniques sometimes get tossed under the heading of econophysics. Traditionally, econophysics is really about stochastic market analysis. It's looking at statistical models of markets. So I want to say a little bit about that and how it's related to the present project. Whoa, there. So stochastic systems include, as a really classic example, Brownian motion. Here you have an example. This is a video of milk globules. Rather, they're fat globules of milk. So you're zoomed in to about 7/100ths of a millimeter across the screen here. And each little shaking thing is a little bit of fat. And they're all jiggling around. When one models this sort of thing, a very typical thing to do is to say the fat globules are following a random walk. Now, random walks can be interpreted in simple senses, and then there are sort of many different stochastic processes that these little fat globules can be taken to follow. But let me just do a simple one, okay? Sort of the first one would learn here. For my purposes, I don't need lots of real complex stochastic analysis. A simple random walk sort of has, each step is roughly the same size. The steps are independent of each other, so whether you're going to move left or right or up or down, it's independent of what happened previously, and the probability of going in any given direction is always the same. This is the simplest random walk. You can imagine lots of variations on this random walk. They're very interesting. Mandelbrot and others have tweaked these assumptions. You can do this. But the simple idea is just like it's like a drunkard, okay? You have the guy where it's not clear where he's going to step next. Okay? You can go forwards, backwards. And you can imagine, you can postulate a drunkard who falls down after so many steps. In fact, we could have a whole pub full of drunkards. They come piling out of the pub, and they all satisfy this random walk. And although you can't predict any given one exactly what it's going to do, you can say with great accuracy what will happen if you have a lot of drunkards. If the whole pub piles out and they all collapse after 20 steps and they're all following random walks, then they tend to distribute in a very regular way. And that is as a normal distribution, if it is the simple random walk. If it's not simple, it can be a more interesting distribution. There can be fat tails, all sorts of fun stochastic phenomena. If you don't believe this, I guess I should have said you can see these slides online. Maybe I'll just write this down for you so you can see. I don't know if I want to let you, I'm not going to waste time simulating this right now, but if you want to go back and look at these, if you go to my website, personal.lse.uk/Robert49/talks/choice, you can find this and follow along. But I'll just quickly show you this idea. Yeah, so that's a random walk. It's not, the randomness is whether it's going to move left or right. And then after a certain fixed number of steps, it's just a JavaScript I've told it to just stop and drop the ball. And you can speed it up if you're bored. And if you let it go for a while, what you find is that you get a nice Gaussian distribution of these things piling up. So you want to convince yourself in an empirical way that this is what happens. Okay. Now, this is a bit suggestive. I've got randomly moving fat globules. It's a very natural thought to look at something like a price in a stock market and say, well, a lot of the same properties may obtain. I don't really know if it's going to move up or down. I may postulate that it with equal probability. Maybe I can use a random walk to describe this sort of thing. However, this cannot represent a price. So here you have something that's randomly walking either up or down. This is the step number going across, and this is its position as it randomly walks away from 0. It's not a good price for lots of reasons. One is that it goes negative after a little while, so that's not going to work. So we don't normally do this. But this thing could represent a rate of return, that R that figured into my equation in the beginning. And this is what we normally do. If I have a Gaussian distribution that comes from a random walk, and I'm using it to model my rate of return, the rate of return is related to the price by an exponent, like this. And if you take this Gaussian and you stick it into an exponent, you get something that is always positive, and it's called a log normal distribution. And this distribution really is found commonly in particular kinds of markets and market dynamics. So this is a more plausible model. We could use random walks to model not the way that a price changes, but the way that a rate of return changes. I once had a master's student who just did this for a bunch of well-known exchanges. So he this is something that was done originally by Osborne in 1959. One of the sort of first jaunts of a physicist into finance was an astrophysicist who did statistics, who reports literally having just picked up the Wall Street Journal and as a statistician thought to himself, that's some interesting data. How would I model this? Not knowing anything at all about it. And the first thing he observed was that the prices were log normally distributed. And what he meant by that was that if you were to count, split the prices up into particular categories. So you've got different share prices going along this horizontal line, 5, 20, 35, 50, etc. And then you count how many shares fit into each category. What you find is that this log normally distributes. And that's sure interesting. Why would it do that? Well, one reason would be that it's accurate or correct to model the rates of return as following a random walk. You notice that not all these exchanges look very log normal. This has this crazy fat tail over here. This one even has a little fat tail. That's the Russell 3000, which is maybe one of the most closely approximating the log normal distribution. There are reasons for that. One can understand and explain that sort of thing. And yeah, that's part of the fun of these models, I think, really. But when you see a log normal distribution, it's sort of a fingerprint that this analysis is working. All right, those were just a couple of models. Not everyone was pleased about this when it was first introduced. Here's an example. This is an investor called Pierre Rinfret. Random walk theory is irrelevant, it is impractical, It is logically inconsistent, it is conceptually weak, it is limited in scope, and it is technically deficient. I feel this is one of the great slanders in all of finance. So not a fan. Wells Fargo, James Verton. You just don't win friends by appearing to tell sincere, dedicated, intelligent people, i.e. investors, that they are useless dolts who could and should be replaced by computers. People warmed up to these analyses. I think these are very commonly used analyses now. The proof's in the pudding, isn't it? If it's working, it's working. And Milton Friedman, he's really writing before these became popular models, before Osborne was writing. But I think he gave the philosophy that many people then use to interpret what's going on here. I take it one of the complaints about this model is that when you look at a price or a rate of return, you don't really think that it's random, right? Things change price for a reason. Things change price because somebody bid on them, or somebody failed to accept a bid, or did accept a bid. These are the things that are determining what the price is, and that has reasons. You woke up in the morning and felt great. I'm going to go get her today. I'm going to buy something, right? And you tried to buy that stock, or you didn't buy that stock. And these complex psychological factors, well, they're complex, but they're not random. So I think a lot of the analysis a lot of the complaints are about this, the randomness part of the random walk analysis. And so in that context, here's a Friedman-esque reply. Friedman says, truly important and significant hypotheses will be found to have assumptions that are wildly inaccurate descriptive representations of reality. To be important, therefore, a hypothesis must be descriptively false in its assumptions. I feel that last bit is sort of a bit of, maybe a little hyperbole. You can find him saying more toned down things than this. But the basic idea is that what matters is the predictive success. If I'm making a bunch of assumptions which are radically inaccurate, that's simply no problem. Bryan? Yes?
So, using choice group rules, I just interject one comment. An alternative way to think about this would be to say, at some underlying micro level, we don't have randomness here, precisely because the various market...
Okay, we're getting there.
At the macro level, you've got emergent stochasticity.
Yeah, you're jumping ahead, that's right. Yeah. So, I think the same, But let me first give another quote, okay? I'm trying to proceed very philosophically here. We'll get there, we'll get to that. There is thus much... Okay, this is, I think, more wisdom from our another local hero for the moment, Dan Hausman. So there is this... this is a response to Friedman, in a way. There's much that may be learned by explaining the components, the assumptions of a theory and its supposedly irrelevant predictions. Such consideration of the realism of assumptions is particularly important when extending the theory to new circumstances, or when revising it in the face of predictive failure. What is relevant is not whether the assumptions are perfectly true, but whether they are adequate approximations, and whether their falsehood is likely to matter for particular purposes. There's lots of interesting examples of this in random walk theory. There's a sense in which random walk theory underpins Black-Scholes analysis. And Black-Scholes analysis, after it was initially introduced, failed to identify an important market phenomenon known as the volatility smile, changes of volatility. And one way to approach that problem, then, is to go back to the assumptions underpinning the Black-Scholes analysis and tweak them. Or if you're trying to do Black-Scholes for something like a cotton market, this doesn't work very well because cotton markets are badly not, they don't satisfy the ordinary random walk hypothesis. So you can go back and tweak that assumption and try and extend the theory in this way. Now, I want to talk about Brownian motion under the hood. This is, I think, going back to Christian's comment. When we model, really the complaint comes down to randomness, okay? But Brownian motion, if you ask a physicist what it really is, it's not really random. We model it that way, but it's not really random. This would be the fact that actually it's a sugar molecule, and so this analysis can also be done with a sugar molecule with little water molecules bumping into it. Sugar molecules are invisible to a microscope, so it's not as good of a video. But I can draw this, and you see this sugar molecule bouncing around. Einstein analyzed this in his dissertation. And although, if you just look at the sugar molecule, it may follow what is well approximated by a random walk. If you can keep track of all these particles, they are moving deterministically, and they're following the laws of classical mechanics. Well, if you want to be more precise, following the laws of quantum mechanics, but it's some approximation classical mechanics. So this isn't really random. Randomness is in a sense just a trick to do the stochastic analysis. Another way to look at this is diffusion described as a random walk. So if I began these particles in a little corner, and then I started them doing a random walk, and what you find is that they diffuse across the whole space. But if you're looking at a real gas, then what you find is something more like this, where you are getting diffusion, and everything is on a perfectly deterministic trajectory, not randomly walking. So we can look under the hood of finance as well. We are often using these stochastic analyses, and we can recognize that, fine, prices aren't really random either. There are complex psychological phenomena, there are reasons that prices do what they do. And that's compatible with the stochastic analysis. So if you do ask that question, then a next nice question is, what is the framework that would be appropriate for describing what's under the hood in finance? Especially, say, if you're looking at stochastic analysis of the kind you see in random walk theory and Black-Scholes analysis and so on. And that's what I want to talk about. So let me turn to that now. So, for those who have a little physics background, I'll tell you just sort of the motivation for what I'm doing here from a physics perspective. There's a very common way to build up quantum mechanics from observational terms. You start just with facts of experiment, and then you start making these bare minimum assumptions, as bare as you possibly can. And what you find through careful building and building is that you get successively more and more structure, and you end up with a theory that brackets a lot of questions about what's really going on, but has enough structure in order to make predictions about microscopic phenomena. That's important because in quantum mechanics we have no idea what's really going on. There's this huge disagreement about how to interpret quantum theory at the micro level. And it works, I think, well in the trade space context as well. We want to say something right and something accurate about financial systems, but I don't want to just, I don't want to assume too much. I'd like a sufficiently broad framework that I could, for example, compare different sorts of approaches to finance, or find that one approach depends on another one. So in physics, this first part of the analysis is called kinematics. And what we're interested in here is, what is a possible state? Well, this is the analogous physical question. Sorry, we'll get to the finance. But the physics question would be, what is a possible state of a physical system? You're looking at a thing. You want to know what its possible states are. So you begin your analysis very often. You go about this in lots of different ways. If you're Newton, you look for the locations and velocities of particles. All of the ways that you can have different locations and velocities describe the possible ways your physical system can be if you're Newton. If you're Hamilton, you have a much more general picture of what classical physics is. You have these generalized configurations and conjugate momenta, and these are what define the possible states of your system. Quantum theory uses probabilistic states, that's the possible states, general relativity, a metric with matter and energy fields. What is a possible state of a financial system? Well, it involves something like an individual trade of something of value, like this book. Can you recognize the cover there? Sort of, you can't see the writing. That's decision theory with the human face being paid big bucks for there, you see. But of course, if I really ask what's possible in an entire market at a moment, it's going to be a lot more than one individual trade. A typical thing that will be happening is all kinds of trades happening in one moment. So when I talk about the possible states of a market, a state will consist in a giant number of trades, a whole bunch of things that happen in an instant, or in a rough interval. All the trades that happen at, say, 8 p.m. in the Dow Jones Industrial or something like that. That would be an example of a state of a market. And there are lots of other states which are possible, maybe implausible. Maybe we've never seen them happen, but we would write down all of the possible states if we could. So again, a trade state is a possible description of all the trades in a market in an instant. And a trade space, I'll take to be the set of all possible trade states in a market at an instant. And that's what a market is, really. That's what's possible in a market, according to me. I'm using the word trade in a very broad way here. So what is a trade? Okay, everything hinges on that. I'll come back to that in just a second, but let me just first identify mathematically what sort of thing I want to talk about here. So when I represent trade space, what is this thing M? M is a certain kind of set. It will be in particular a smooth manifold, and it will have a symplectic form with it, which is a gadget that lets you take another kind of object called an observable, any smooth function, and turn it into a vector flow on the manifold. It's a gadget for giving you symmetries, transformations that conserve a quantity. It's a gadget for determining a dynamics when it comes to doing that. And it is, from a classical mechanics perspective, is the most general way of looking at Hamilton's equations, which are a generalization of F equals ma. But in the simple terms, M is, M contains a set of all the possible trade states. When you come to interpret this object, yeah.
So, and then omega would be the set of all possible trajectories.
No, omega is a two form.
Okay.
Yeah, so it's a mapping. It is literally this is a manifold that admits things like vectors and covectors in the tangent space. This is a field, so it's defined at each point in the manifold, and it is a mapping from a pair of vectors to a real number that has certain properties. It's antisymmetric, it's closed, it's non-degenerate. Those are all very mathematical things. I think there are lots of ways to, there's lots of ways to motivate a symplectic manifold, though. One can view it as, one can begin with assumptions about how symmetries in the system ought to behave. And so there's, I think, maybe a lot of nice mathematical ways that one can motivate this that I won't go into, but we can talk about in questions if you like. But this is the tool I'm going to use. And I wanted it in particular because it helps me build the dynamics in a nice way. So before that, just to interpret this a little bit, I want to have a thin and a thick, well, just to illustrate how broadly you can interpret trade space. Here's one thin interpretation and one thick interpretation. Okay, you sort of see what I mean. I think I got these words from Christian, though, so thanks for that. The thin interpretation, in a sense, it's less plausible, easy to manipulate, though, and it'll help you understand what I want this thing to do. So write each trade state in these special coordinates, where I've got a whole bunch of Q's, Q1, Q2, Q3, blah, 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 up to Qn. I've got a bunch of P's, P1, P2, blah, 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 up to Pn. Mathematically, I can always do that. A thin interpretation of S would say something like, S describes exactly in trades, individual trades, in total. And I could number them, I equals 1, 2, 3, blah, 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 up to n. And each pair, Q and P, so Q sub I, P sub I, they represent a certain thing. They represent the quantity and the price associated with the ith trade. So I have a very simple picture of a market now, which would be of interest if you were doing what's called technical analysis, where all you really care about are the prices and quantities at a given moment. And all your analysis comes out of this sort of thinking. So in this analysis, an individual trade just has a quantity. I give you some amount of stuff, and I charge you a certain price for that, and you give me that money in return. And then I've got a whole bunch of those that happen in a market in an instant. Yeah?
Do we have just a single thing being traded, or are these prices of different commodities?
They could be all different commodities. And in fact, I won't even say at this stage whether or not Q1 is a certain quantity, Q2 is another quantity. They could be the same quantity, or they could be different quantities. At this stage, I won't even say such a thing. But if, for example, you wanted to express something, this language does let you say interesting things about, for example, no arbitrage. If you wanted to express something like no arbitrage, you would want, in the sense that you want all commodities to be traded at the same price everywhere in the market. You wouldn't want one of these slots to have a certain quantity going for a certain price, and another slot to have the same quantity going for a different price. That would violate no arbitrage. So at this stage we haven't said it, but one can write this condition down, study its properties, and I think one of the nice things about the framework is that it's so general, it lets you state no arbitrage market dynamics as just a special case of this more general picture.
So, can I just ask
Yeah.
a clarification question? So, I guess what you're building, like, there's flexibility here. That so you are incorporating the possibility that the quantity to price relationship isn't linear.
Yeah, it could be anything here. Yeah. Yeah. Yeah, but if one wants, we can add those sorts of assumptions. You can add market clearing assumptions. You can add all sorts of things. And that's particularly relevant when it comes to trying to define the dynamics.
Yeah.
If you wanted to recover neoclassical economics, it will come out as a particular a class of dynamical trajectories on this picture, and it'll make assumptions like market clearing assumptions and setting a sort of a maximum budget value for individuals in the market.
Just a quickie. The point about Hamiltonian mechanics is that it's all about energy.
Yes.
And and P and Q are a very special thing in physics, right? Like momentum. So you haven't mentioned energy yet. You're going to mention.
Yeah, I'll talk about it in the dynamics a bit, but I guess I could say something about it. Energy is, in the most general sense in Hamiltonian mechanics, what it really is it is the generator of time evolution. So if you want to know how things change, it is energy that generates that. There's a particular mathematical schema for that. And the special feature of it is that energy is conserved as you then go along that dynamics. Now, in the abstract, trade space doesn't have to be interpreted as position and momentum at this stage, or something like position and momentum at this stage. I will get to saying something about how it compares to classical mechanics in that way, and I'll say something about the formal definition of energy as well when we think about the dynamics. Yeah.
So from M and omega, can we already read off what the dynamics is, or do we need to specify the dynamics separately?
You need to specify the energy. You need to specify a Hamiltonian.
Okay.
Yeah.
So M omega plus the Hamiltonian
will then give you a dynamics. Yeah. Yeah, and those different energy functions will correspond to things like having no market forces, the original example we did, having particular, market forces corresponding to neoclassical economics, and so on.
Can I just ask one more question? Sorry. I see there's some sort of project of establishing some sort of formal analogousness here. Now, it seems to me that the trades themselves aren't as such in the space. It's more that you can locate trades by their price and quantity. Is that right to say that? So I really don't know what I'm talking about when it comes to physics. But the maths isn't itself, like the objects themselves aren't in the space. It's more that you locate them by virtue of their properties, by their properties.
Are in the space. I guess maybe you're asking something about how it is that I come to observe a trade state. Is that right? Like, how do I know something about a trade state?
Well, it's more like the trades aren't really things in this. Maybe I'm really dramatically showing how little I know about this subject. But trades don't seem to be there, right? All you can do is locate a trade by its price and quantity.
Okay, yes, I'm not physically describing that it was you as opposed to somebody else. That is a matter of interpretation in this system. But it would be analogous to saying, yeah, good. So similarly, when one describes a system of particles in physics, I don't say lots of personal details about the individual particles. I will give you a list of properties. I'll say I have this position of momentum, and I have that position of momentum, and I have that position of momentum. And if you say to me, but there are other properties that I care about, then what you're saying is this thin interpretation is not enough for me.
Okay, got you.
And then what you want is the thick interpretation. And now the thick interpretation, this I say again quite generally, take the same initial point. I've just got, again, a trade state, all the individual trades in the market in an instant. And I can again, this is a mathematical fact that I can write them down in this coordinate form. But a thick interpretation would say something a little bit richer. It would say something like, these values, Q sub I and P sub I, really represent a variety of further facts relevant to the description of the trade S, or the trade state S, I should say, in addition to the quantities and prices. such as facts about the mental states of the traders. So if you were somebody who were incorporating behavioral economics into your analysis and you wanted explicit variables for the dynamics of individuals, if you were trying to incorporate rationality or something, you know, it could fit in this framework because you have variables that can represent anything you want. In this framework, it's not telling you that much. I'm just sort of highlighting that you can do this at various levels. So there's varying degrees of thickness. It's not one thick interpretation, one thin interpretation of the formulas. How does one observe things in any context? Well, in statistical context, you sort of want to collect a lot of examples of data and produce long-run frequencies that you maybe associate with probabilities or other statistical properties. But in this context, I'm going to assume we're operating with facts that you can just read off. There are some such facts about a trade event, especially if I'm talking about the Russell 3000 or the S&P 500 or some such. Of course, I can just read off something like the total market capitalization in pounds. I can just write down how much money, add up all the prices in the entire market for all the shares, add all that up. I'm going to get a number. And at every moment, I can look it up on a list. I might be a bit behind because it takes me a while to do the calculation, but in principle, I could write down a number at any given moment associated with this particular fact. And that is normally our situation in these sorts of classical scenarios. Even when you're collecting data for a stochastic analysis, you have to have outcomes that you then use to produce relative frequencies. And those outcomes are normally associated with just a real number. You take a state of your system and you associate it with a real number. What does that real number represent when you're observing something? I could be observing someone in a certain position, that you're sitting there, and I'll draw a number line across the room, and that position would turn out to be 4 on my number line, this one 5 and 6. Then what I'm doing when I'm assigning positions to you, or I'm assigning a number to these different states that can be occupied by people in the room. And I'll treat financial states similarly. So these trade states will have functions which take each trade state to a number, and that number will represent a magnitude that you've observed. The magnitude may have many different interpretations. There's lots of magnitudes out there. You may have many different ways of measuring these magnitudes. But this is just an abstraction characterizing what it is for a classical observation to be made. And it corresponds to, again, the classical mechanical concept of observable in classical physics. So mathematically, how we do this is we'll take, this is what I said, tau to be a function from each trade state to a real number. Interpretively, we'll represent the sum of all the amounts traded in the market at that instant with this number. And we write it like this. Tau is a mapping from M to R, and I'll take it to be a smooth IDC infinity function. This, again, is just a matter of terminology, really. By definition, I will call such a smooth function a financial observable. I mean, there's further questions, I think, especially in the Friedman context, about whether any of these things are really that observable. I think some of these are, because market capitalization is observable. But just because I've written down a function doesn't mean I can find a way to measure that thing I wrote down. So in general, there's some art in the modeling and the choice of observables.
Just to back up to this point, a total market cap for a firm or for the whole market?
For what?
For a single firm or for the whole market?
Uh-huh.
When you say total market capitalization, do you mean for a single firm or do you mean for the whole market?
You could have either one, right? Yeah, sorry, I just didn't hear the word firm, right? So yeah, I could have market cap. Often when you're seeing it listed, you're associating it with a particular security. That will be a real number assigned to every state of the market, right? I mean, this is how general it is that the state of the market is everything that happened in that moment. But one of my observables will be, what is the price of Apple right now? Or what are the possible prices of Apple? And there will be an Apple function, which is telling me just the price of Apple, and it's therefore ignoring a lot of the information that's contained in the state. It's just that it's extracting one bit of information. This could be a function that, I think here what I meant was add it all up. So I've got a market with a finite number of securities. I add up all of the market caps, and especially with all the firms, and I get this number. But of course I have individual ones as well. They're just a bunch of smooth functions. So this is a really rich collection of functions available to me.
And when you say the amounts traded at an instant, are you thinking of trades occurring in continuous time?
I will, yeah, roughly, but I don't. That I'll get to. That I want to treat counterfactually, really. I mean, so there is this fact that we make all our observations about markets in finite instance, and trades, even worse, only happen at finite instance rather than in continuous intervals. But we can always ask the question: if a trade would have occurred at that time, what would be the values of the variables associated with it? And that's more of a dynamical question. Right now I'm just asking what's possible at a given instant. If you ask how things go from instant to instant, that's the dynamics bit, so we'll get to that.
Right, which I mean, the reason I'm a bit confused about the second one is, so these instances are discrete for the purpose of the second one, because if it was continuous, my thought would be that any particular instance would be no trades if trades occur at a specific point in time is continuous, then at any particular point in time there's no trade taking place at that particular precise
Okay,
point.
well this is an objection for the next section, but I mean, again, maybe I'm not communicating well, but the way I want to think about it is, if I have a trade event at one time t,
Yeah.
and another trade event at a time t prime, and those are things that actually happen. So here a trade happened, and there another trade happened. And, you know, because we don't do things all the time, there is this space in between when nothing really happened. But I will, in the end, describe a continuous dynamics for the system. And how I understand that is, in this, you know, dynamics here will take me deterministically from a given trade state to a later trade state. And so supposing that I know this initial trade state, what's going on in here, how I'll interpret it is just to say, if a trade would have happened in this instant, it didn't, but if it would have, then it would have been assigned a particular price, quantity, psychological state, etc. So it's analyzed counterfactually, although nothing really happens. And this is to give, you know, why not do that, I suppose. That's how I feel about it. Yeah.
Yes, it's pretty clear that such a function always exists, but in order to do that, we need to guarantee uniqueness, right? Because then
Of what?
Of only one such function being able to fit the n to r relationship.
Yes, and of course there won't be a unique, so if I've got just a, yes, so if I have a discrete set of data points, there are actually infinitely many smooth functions which will fit those data points. That's correct. But, well, there will be one right one, I suppose. I mean, if I ask counterfactually, what would have really happened? In a deterministic system, these sorts of questions have meaning, right? If it's really deterministic dynamics and I start with an initial state, then it will be guaranteed, you know, whenever the next trade happens at a given time, it'll be guaranteed what happens next. And so it will be equally guaranteed what happens in between, insofar as, you know, this is like a counterfactual statement anyway. One thing you'll observe, one thing I'm comfortable with this framework is that you will find that the same dynamics is modeled by many different dynamical systems, often infinitely many dynamical systems. That's actually a virtue of this theory, really. I mean, there's a whole theory of perturbation theory in classical mechanics where you start with a nice easy dynamics as something that you know and understand and are familiar with, but it's not quite accurate. You can then consider a perturbation of that dynamics and make it more accurate. And this theory is well developed and rich and lets you do all sorts of nice things. And it trades exactly on this fact that, well, there's a lot of dynamics in the neighborhood of what's actually going on. I just need to pick one that's close enough. Here again, I refer to Hausmann's wise words. It doesn't have to be exactly right once and for all. What's interesting is your degree of approximation. All right, these are just a few more concepts on the kinematics. Price, log price, and momentum. This is really in part to illustrate the special role that price plays in the system, and it makes a connection to ordinary classical mechanics as well that I find helpful. Here maybe there's an interesting interpretive thing too, so let's see. So price in this system really, no matter whether I'm using a thin or thick interpretation, could always be viewed as this smooth function. It'll take a trade state to a real number. So it will be referring to price of a thing, of a particular thing that was traded. maybe by a certain person even, if I've got a system with arbitrage, so there's different prices for different traders. So I have this smooth function from the manifold to the positive real numbers, and I'll call it price. I'll often be interested in this other quantity, log of the price. I'll say something about why. I'm going to have a minor shtick about this. Well, really, there's lots of reasons. Maybe we can talk about it more in questions, exactly where this log comes from. In the stochastic analysis, I think there's lots of, Osborne gave lots of really interesting proposals for how to understand this. But one reason is that it works well to look at, it's helpful to look at this quantity pi. So that's always defined because p is positive. Now I want to draw on, I think, an assumption about markets which is plausible. And maybe it's a fact about markets. I don't know. Philosophers can tell me how to treat this assumption. When you're assigning prices to items in a market, there is a certain symmetry associated with that assignment of prices. And that symmetry is the replacement, intuitively, is the replacement of one currency with another. So I may be selling widgets in pound notes, but I can turn around and sell widgets in dollar notes or in euros, and I can design an identical system, a system related to the original one by a symmetry that doesn't lose the essential information about what the market is describing, what trades the market is describing, and how the dynamics of that market work. So this is not a claim about currency markets right now. Okay, this is a claim about arbitrary trades. Imagine trades in the Dow Jones Industrial or something like that. They would normally be written in dollars, but in order to express them easily to myself as a trader with my budget, I might have a computer that just generates the whole script that generates the whole market value, all the market values in pounds. This is a symmetry of the system. If it's a symmetry of the system, then I can write it down in a particular way. I'm using a particular tool to represent my system. It's a symplectic manifold. And I'll now write down this transformation in this way. I've written e to the, so I've got an initial price, and I'm going to transform it to a new price related to the first by this e to the k. That is always possible because, price is always positive, and this currency symmetry will respect that by guaranteeing that this constant is always positive as well. So when I describe the currency symmetry, I will write down this transformation and then say it is a symmetry, and what that means is that it preserves all the structures in the gadget that I'm using to represent things. So I have a manifold and I have a symplectic form. It should be a smooth diffeomorphism to preserve the structure of the manifold, and it should be symplectic transformation, which means it preserves the symplectic form when you pull up to describe the symplectic form. The sort of simpler way to think of this is that any dynamical laws that I were to write down using these structures would be preserved under the symmetry. So if a trade dynamics could happen in the first description, say with dollars, then the same trade, an analogous symmetric trade dynamics would happen in the new currency.
So that would mean, if we consider the space of possible trajectories of the system under a given dynamics, that space would be closed under
yes, exactly.
Those
yes, exactly. What a symmetry is it preserves the trajectory space. That's exactly what it is. And a symplectic transformation implements that in this context. Then I'll just, whoops, sorry for the failed LaTeX there. Then there is this mathematical fact that follows from this, the fact that this is a symplectic transformation. I'll just say this quickly because I didn't want to go over all these technical details. But really, for every real number, for every positive real number, I have a symmetry like this. So there's lots of different currencies I could invent, even if they don't happen to exist. And I'll want this symmetry to hold everywhere. So what this really is a one-parameter group of symmetries. And a one-parameter group of symplectic transformations always has a generator. I'm going to call that generator mu. It is also a smooth function, and in classical mechanics it gets interpreted as momentum. It is the generator of translations. I mean, another way to view what I'm doing here is this transformation is equivalent to, if I look at that pi that's the log of the price, pi of s maps to pi of s plus k. So if I view pi as something like position, then what this currency symmetry is doing is it's like translating you around in position space. And this is a common way of deriving momentum. If you want to know what momentum is in physics, you often say it is the generator of translations. Suppose your system has a translation symmetry, then there will be momentum. And it just comes out of formalism in this way. And how you know it's momentum is that it satisfies this relation with the Poisson bracket. That should be a Greek pi, not written pi. And mu, the generator for momentum. And they are equal to 1. And this is the classical mechanics of position and momentum. All right. I have maybe 5 minutes left in the official talk, so I will just say a couple of things about the dynamics, and then stops for questions. So when one generates a dynamics in this classical mechanical system, you only need one thing, as sort of came up earlier. You need an energy function. You have a smooth function, which is something that you take to be conserved, and it'll tell you uniquely, given any initial trade state, what the future trade states will be. Why suppose that any such thing exists? Well, if it accurately models the way things happen. If there really are reasons that the market proceeds from one event to the next, then we ought to be able to write those reasons down and accurately model them. Or another way to put it is, if you believe that the right way to think about stochastic market dynamics is in terms of a probability distribution on real possible trajectories, then we want to write down what the real possible trajectories are. Now, they might not be perfectly accurate, but we can write down approximations in various circumstances. In this context, you can write down simple ones like, maybe here I'll just put this up. And maybe if I do what Alex did before, yeah. So the really simple case that we started with was one in which we had a dynamics that basically only respected the time value of money. You would expect to be able to write that down in this formalism, and you can. And what it looks like is something, very similar to something we often see in classical mechanics. It looks like what's called the free particle Hamiltonian. This thing is just something I would write down, but again, when you if I have more time, I'll go through this calculation. When you run through this calculation, what you find is that this Hamiltonian generates for you a price that goes as P of t equals your initial price times e to the RT for some constant r. How does it generate it? This comes out of that symplectic form. So the symplectic form is really a gadget that will for every h, give you a vector field. So this object together with h will give me a vector field x sub h. And if I imagine my big trade space as a big grid like this, what it's really doing is it's telling me, given an initial point, what the future trajectory will be like. And I can feed at any point I want, and it'll tell me what that trajectory will be like. So this x sub h is this vector field here. More interesting ones include if I were to look at a harmonic oscillator. This is an object that describes any analytic function. If I look at it in first order approximation and it's stable in a certain sense, I can write down a Hamiltonian as something called a harmonic oscillator. This gives rise to a bunch of, it looks like this. This object gives rise to trajectories which have a certain stability property. They look like little rings in phase space. Yeah, I could maybe carry on about this, but I think I'll stop here and take questions, but maybe just a couple of final comments. Thin and thick trade spaces are the sorts of things that are maybe would be described as two different symplectic manifolds, two different manifolds. If I'm interested in something like inter-theory relations, then I might look for an embedding from one manifold into another. This would tell me something about how, if I wasn't correctly modeling something with my thin interpretation, that the reason might be that there were just other variables that were relevant that I was ignoring. And by moving to the larger space in which this thing is embedded, I could recover a correct description of the system. Another question I have about this is extensions of classical finance. One can write down Hamiltonians again that satisfy certain market clearing properties that allow you to derive expressions familiar from classical economics. If one were interested in extending this sort of thing, you can use this framework in order to explore these expansions, these extensions. You can take a Hamiltonian and perturb it, or you could do something weird like ask whether or not this classical theory can be quantized. That would require a certain interpretation that I think I've spoken with Frank and some people here about before. I'm not really sure what would motivate that interpretively, but it's a question we can ask. And there's a lot of other questions we could ask, but maybe I'll stop here. So thanks for your attention.